Hello students, so in this particular video we'll discuss the important examples and exercise of chapter number 2, electrostatic potential and capacitance. These sums are very frequently asked in your board exam. See example 2.2 of your textbook. The question says two charges are located 15 centimeter apart. There are two charges, 3 into 10 raised to minus 8, minus 2 into 10 raised to minus 8. They are located 15 centimeter apart. Okay. What point on the line joining the two charges is the potential 0? Take the potential at infinity to be 0, because we generally deal with the potential difference. That is why they mentioned that the potential at infinite to be 0. Okay, so you have to find the points where the potential due to both the charges will become 0. Okay, since potential is a scalar quantity, potential due to this positive charge will be positive, potential due to negative charge will be negative. So if both the charges are of equal magnitude, the point will lie somewhere the midpoint, somewhere at the midpoint. Okay. Now let us consider the point, since 3 is greater than 2, so the point will be towards 2. So somewhere here, right? Let this distance be x. The point can be here also, that means internal point, external point. We will discuss both the cases, right? So case 1, let us assume at the point P, potential due to both the charges will be 0. So potential at point P will be potential due to plus charge plus potential due to minus charge. According to the question, you have to find the distance where potential becomes 0. So potential is 0. Potential due to positive charge. What is the potential produced by a point charge? KQ by R. You don't have to put a vector sign because potential is a scalar quantity, right? So K into 3 into 10 raised to minus 8 upon R. That means this distance is x. So this will be 15 minus x, right? Plus K into minus 2 into 10 raised to minus 8 upon 15 minus x. Solve this. Let us take this term over left side. So it will be minus 3 into 10 raised to minus 8 k by x equals to minus 2 into 10 raised to minus 8 k upon 15 minus x. So this will be minus gets cancelled. So this will be cross multiply. 45 minus 3x is equals to 2x, right? Multiply this term. So 45 is equals to 5x. So x equals to 9 centimeter. Clear? 9 centimeter from positive charge, right? We'll see another case where the point is lying outside the line joining the charges, right? Okay, now case 2, where the point P will be lying outside the line joining the charges, right? That means this was 15 centimeter. Now let us consider the point P here outside the line joining, right? Clear? Let us say this as x. Okay. So once again, potential at P will be because of positive charge, negative, right? 0, we want the distance where the potential due to both the charges will become 0. Potential due to positive charge will be K into 3 into 10 raised to minus 8 upon 15 plus x, right? The total distance, 15 plus x, plus K into, okay, clear? Solve this. Minus 3k into 10 raised to minus 8 upon x plus 15 equals to minus 2k into 10 raised to minus 8 divided by x minus minus. So 3x is equals to 2x plus 30, right? 3x equals to 2x plus 30. So x is equals to 30 centimeter. X is 30 centimeter from negative charge. So from positive charge it will be 15 is greater than 30, but that's okay. This is 15, this is 30. So total distance will be 45. So we have got two distance, right? One was the point was lying between the line joining the charges and outside, right? So 9 centimeter or 45 centimeter from 3 into 10 raised to minus 8 coulomb charge. Clear? This is your answer. Okay. Now next one. Okay. Now example 2.4. So in this question we have been asked to calculate. See, the question is 4 charges are arranged at the corners of a square ABCD as shown in the figure. You have to find the work required to put together this arrangement. Square of side square each of length d, right? And charges q, minus q, q and minus q are arranged at ABCD corners of a square. You have to find the work done to put this arrangement together. Then charge q0 is brought to the center E of the square. That means a charge q0 is brought here at the center E. So how much extra work is needed? Okay, so first of all we have to calculate the total work done to make this arrangement possible. And then when a charge q0 is brought at the center E, then what is the extra work needed to put the charge here, right? So these are the two questions. Okay, so in the topic of potential energy of the system of charges, we have already discussed the formula and we have understood the concept, right? That means suppose when I am bringing the charge q at point A, first I am bringing this charge. So to bring this charge there is no work needed to be done, because work needs to be done against the electric field of some another charge or against the potential of the charge. But since there is only one charge q, first I am bringing this charge which is placed at A. I have brought this charge from infinite. Clear? So to bring this charge no work is required to be done, because there are no other charges. Only one charge is present. So there is no electric field of other charges. There is no potential produced by other charges. So work need not to be done. So work done to bring a charge A will be 0. Clear? But when you are bringing the charge minus q at B, now you have to perform some work, because when a charge is placed at A, it will produce some potential at B. Clear? So work done to bring the charge at point B will be charge multiplied by potential of A. Potential of A on B multiplied by charge q into B. So that will be minus q. What is the potential of A? Kq by R. Point charge will produce a potential Kq by R. So this will be Kq by R D. So work done to bring the charge at point B is minus Kq square by D. Clear? Clear? Similarly, when you are bringing the charge plus Q at C, then work needs to be done, because now both the charges will produce some potential here. Potential of A at point C, potential of B at point C. Both the charges at A and B will produce some potential at C. Clear? So work done to bring the charge at C will be charge at point C into potential of A plus potential of B. That is Q into potential of A. A is placed here. This distance will be root 2 D. D, this is D. So according to Pythagoras theorem, this will be Kq by root 2 D. Right? And potential of B will be minus Kq by D. I am using the formula kq by r because for a point charge potential is kq by r. So work done to bring the charge will be, to bring the charge at point C will be kq square upon root 2d minus kq square by d. Clear? Okay. Now to bring the charge at point D, work needs to be done against the potential produced by three charges A, B and C, right? So work done to bring the charge at point D will be minus Q into potential of A, potential of B, potential of C. Clear? All these three charges will produce some potential at point D, right? So minus Q into what is the potential produced by the charge placed at A on D. So this distance is D, charge at A is Q, so it will be kq by D, right? Okay, potential produced at D because of charge placed at B will be minus kq by, this distance will be root 2D. Clear? And potential produced by the charge at C will be kq by D. Clear? So work done to bring the charge point D will be minus kq square by D plus minus it will be plus kq square by root 2D minus kq square by D. This is the work required to be done to put the charge at D. So what will be the total work done? Total work done will be A, B, C, D, addition of all this work, right? That means total work done will be, total work done for this arrangement will be work done to bring the charge at A, B, C and D. Fine, work done to bring the charge at A is 0. This will be minus kq square by D, and work done to bring the charge at C, this is plus kq square by root 2D minus kq square by D. Clear? And work done to bring the charge at point D will be minus kq square by D plus kq square by root 2D minus kq square by D. Clear? This is the total work done to get this arrangement. Okay, fine. Now simplify this, solve this. Kq square by root 2D, kq square by root 2D. So that will be 2kq square by root 2D, right? Then minus kq square by D, minus kq square by D, minus kq, so that will be minus 4kq square by D. So this can be still, this will be root 2 kq square by D minus 4kq square by D. So I will write it as, I can take kq square by D as common, root 2 minus 4. This is the work done. Clear? Right? And what is the extra work needed to bring the charge Q0 at the center? Okay, so extra work will be work done to bring the charge at E will be charge multiplied by potential at E. Clear? Potential at E, that means potential at E because of A, because of B, because of C and because of D. See, work done will be 0 because let this distance, let us say it as R. So this will be R, this will be R. Clear? See, the potential at E will be kq by R minus kq by R plus kq by R minus kq by R. Right? Potential at E will be the sum of the potential produced by each and every charges placed at the corners. Clear? This charge is positive, this is positive, so their potential will be kq by R, kq by R, kq0 by R, kq0 by R. This will be minus kq0 by R, minus kq0 by R. Total will be 0. So potential is 0. So work done to bring the charge at the center will be 0. Clear? Okay, we will solve another question. Another example, example 2.10. A 900 picofarad capacitor is charged by a 100 volt battery. Capacitance is given 900 into 10 raised to minus 12 farad, and it is charged by a battery of 100 volt. Fine. What is the energy stored by the capacitor? The capacitor is disconnected from the battery and connected to another 900 pf uncharged capacitor. What is the energy stored by the system? Fine. So in the first part of the question, you are being said to calculate the energy of a capacitor whose capacitance is given and voltage is given. So we know that energy stored in a capacitor is half CV square. So this will be half 9 into 10 raised to minus 10 into 10 raised to 4. So this will be 4.5 into 10 raised to minus 6 joule. Clear? Clear? Now, in the B part, they are saying that you are disconnecting the capacitor with the battery. That means you are removing the battery and you are connecting another identical uncharged capacitor. Okay, that means now this is already charged. Let Q be the magnitude of the charge, and now I am connecting this with an identical uncharged capacitor. So when you are connecting a capacitor of any charge Q with another identical uncharged capacitor, charge will be equally divided. That means this capacitor is having some potential V, which is of 100 volt, right? And this is uncharged. So this capacitor's potential will be 0. This is having 100 volt, right? But whenever you are connecting a capacitor with another uncharged identical capacitor, charge will be equally divided, right? That means charge from this capacitor, it will flow until the potential becomes equal. So one is having a potential V, another is having 0. The charge will flow until the potential becomes equal, right? That means now this capacitor will have a charge Q by 2 from 0, and this capacitor will have a charge Q by 2 from Q. Clear? So now both the capacitors are having a charge Q by 2. Okay. So energy stored will be U1. U2, we have to calculate the energy stored by the system of the capacitor. That means this energy plus this energy. So U1 will be Q by 2 the whole square upon 2C. Clear? So this will be Q square by 8C. U2 will also be equals to Q square by 8C. Clear? So total energy of the system will be U1 plus U2. That means Q square by 8C plus Q square by 8C. So that will be Q square by 4C. So this can be written as Q square by 2 into 2C. But what is Q square by 2C? This energy. So energy of the system will be half of 4.5. That means 4.5 into 10 raised to minus 6 divided by 2. This will be 2.25. Clear? This will be the energy of the system. Right? Now we will solve the questions which are given in your exercise. These were all the important examples of chapter number 2. See, first question of your exercise, 2 charges 5 into 10 raised to minus 8 and 3 into 10 raised to minus 8, minus 3 into 10 raised to minus 8. The same question we had solved in we have solved in the illustration, only the values are different. No problem, but we will solve this question. There are 2 charges 5 into 10 raised to minus 8 and minus 3 into 10 raised to minus 8. They are located 16 centimeter apart. This distance is given 16 centimeter. Find the potential, at what points on the line joining the 2 charges is the potential 0. Take the potential at infinity to be 0. Again the same thing. right? You have to find 2 points where the potential due to both the charges should be 0. One will be the line joining the two charges, anywhere between the line joining two charges, and another point will lie outside the line joining the two charges. Clear? Fine. Let us take the point P here. Let this distance be x. So this will be 16 minus x. This is your first case. Potential at point P will be potential due to positive charge, negative charge. Clear? Clear? You have to find x where potential becomes 0. This will be 0. Potential due to positive charge will be k into q upon r. Potential of a point charge is kq by r, plus k into q upon r. Solve this. Minus 5k into 10 raised to minus 8 upon x equals to minus 3k into 10 raised to minus 8 upon 16 minus x. Right? Minus minus gets cancelled, k gets cancelled, 10 raised to minus 8. Okay, multiply this. 80 minus 5x equals to 3x. 80 equals to 8x, right? So x equals to 10 centimeter. So first distance is 10 centimeter from 5 to 10 raised to minus 8. Right this way, x equals to 10 centimeter from 5 to 10 raised to minus 8 coulomb charge. Clear? Right? This was case 1. Now let us discuss case 2. Now we will take the point, we will suppose the point outside the line joining the charges, right? Fine. Let us take the point somewhere here. So this will be x and this will be 16 plus x. We will solve in the same manner, only you have to this. So potential at point P, positive charge, negative charge. 0, k, q by r. R means 16 plus x, the total distance, 16 plus x, right? Plus k, q, r. Solve this. Minus 5k this will be 5x equals to 3x plus 16. Cross multiply. Clear? No, sorry. 5x equals to 3x plus 48. So 2x equals to 48. X equals to 24. 24 centimeter. So total will be, okay, 24 centimeter from minus 3 into 10 raised to minus 8. Clear? Or total will be 24 plus 16. So it will be 40 centimeter from 5 into 10 raised to minus 8. Clear? Okay. Now we will solve another question. Okay. In another sum, a parallel plate capacitor, exercise 2.5, a parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. Parallel plate capacitor, air is a dielectric, so the capacitance is 8. What is the formula for finding the capacitance of a parallel plate capacitor? We know that it is epsilon naught A upon D. Now, what will be the capacitance if the distance between the plates is reduced by half and the space between them is filled by a dielectric constant 6, a substance with dielectric constant 6. Okay. So beforehand, when the distance between the two plates was D, capacitance was 8. Now you are reducing the distance to half. So now the distance is D by 2 and the medium is filled with a dielectric constant, a substance of dielectric constant 6. when capacitor, when you are introducing a dielectric slab between the plates of the capacitor, capacitance increases by k times, right? So new capacitance C dash will be k times of C. That means k times epsilon naught A upon D by 2, because the distance between them is reduced to half. So this will be C dash is 2k epsilon naught A by D. What is epsilon naught A by D? 8. So it is 2 into 6 into 8. Clear? So this will be 96 pf. Fine, right? So now in the next video, we'll discuss the important points and important theories of current electricity.